So before we can really talk about how to interpret the derivative graphically, I have to make sure that we understand how to figure out the slope of a tangent line just by looking at it. And so that's sort of what the beginning of this video is going to be about. So I have a picture for you here, right? What I did is I drew a bunch of lines, all with different slopes, right? And in particular, this black line in the middle has a slope of 1, right? It makes a 45-degree angle with both the x-axis and the y-axis. And that's something that I expect. Like, I expect us to know that if you see a line that sort of has a slope that looks like it's at about a 45-degree angle, that's a slope of 1. Right. Now all these red lines, this is a slope of 2, this is a slope of 3, slope of 4, slope of 5. To be honest, those all look similar to me. Like if you were to pick any one of those and ask, oh, is this a slope of 2 or 3 or 4 or 5? I don't really know. What's important to me is that because these lines all are steeper than the 45-degree angle line, these all have a slope that's greater than 1. Right. Similarly with the green lines, right? This is all, this is a slope of 1/2, 1/3, 1/4, 1/5. The thing that's important is that all of those green lines have a slope that's less than 1. And so my hope is that when you guys see tangent lines, you'll be able to sort of picture this thing and sort of think, is the tangent line that I'm looking at, does it look like a 45-degree angle slope? Does that look like a slope of 1? Does it look steeper than that, meaning that it's a slope of 2 or maybe 3 or 4? Or is it less steep than that? Is it a shallower slope than that? Is it something down here where it's, a half or a third or a fourth? I could have done another picture just like this for all the negative slopes, but I really didn't want the video running longer. If I were to take all these things and just shift them into being negative slopes, the exact same thing would happen, right? Things that are steeper than -1 will be steeper, and -2 or -3 or -4. Lines that are less steep than -1 would be things like -1/2, -1/3, -1/4. So keep in mind the ability to sort of estimate slopes. And we're going to get to that practice of estimating slopes in just a second. But before we can get to that, we do need to recall from some of our earlier lessons, what does h prime of 2 actually mean? Like, what's the significance of h prime of 2? Now pause the video and think about that for a minute. Make sure that you still have that idea in mind. So remember that the significance here is just that h prime of 2 represents the slope of the line tangent to h of x at x equals 2. So if someone were to ask me what's h prime of 2, I need to come up with some way of telling them the slope of the tangent line. And in this video, and in the following one, we want to start looking at how we can do that using a graph. And so, as an example, here I have the graph of g of x. And what I want us to do is sort of go through and figure out for several points, what is g prime of -2? What is g prime of 1? What is g prime of 2? Like, what are all these things? And remember what these things represent. Remember that these things all represent the slope of the tangent line at different places, right? So, what is g prime of -2? Right, well, how do we answer that question? When we go to our graph over here at -2, we go down to the function, and then we either physically write or we visualize what the tangent line looks like. Right? So that's roughly my tangent line. Now, think back to the picture with the green slopes greater than 1, the black slope that was a 1, and the red slopes that were less than 1. What does that slope look like? Does that look like it's a 45-degree angle? Does that look like it's a slope of 1? Like, to me, that slope looks like it's a little bit steeper than 1. And so we might estimate that g prime of -2 is something like 2. If you said 3, that's fine. If you said 1, like maybe, but that line doesn't look like a slope of 1. I mean, in fact, even you have the grid lines here. The grid lines here would tell you that a slope of 1 should be going right between each of those. Like, we should be going, up 1 over 1 as we're going through and finding this thing. Okay? Now, let's keep going. What about g prime of 1? Right? G prime of 1, so we're right here. That's at the very top, which means my tangent line appears to be horizontal. And if you have a horizontal tangent line, that means the slope is 0. Okay? Pause the video, try g prime of 2 and g prime of 1.2 on your own, and then we'll sort of check answers together. So g prime of 2 means that we're going over to 2, and sort of drawing our tangent line here. That one to me looks a lot more like that slope of 1. But because the function is decreasing as I go from left to right, that's a slope of -1, right? 1.2 is kind of an interesting one, and I know I don't have a lot of space for it, but this is almost like a mental exercise. If you think about the point right here at 1.2, just past that maximum point, and you were to try and draw a tangent slope there, the idea is I really have no idea exactly how steep that line is. But I can tell you for sure that it's not very steep. It is negative, and it's a fairly flat slope. Like I would guess probably 1/3, maybe 1/4. If you have anything that's less than anything that's, -1/2, -1/3, -1/4, those would all be acceptable there. And then my last question is one that you need to think about. Which one is greater, g prime of -3 or g prime of -1? And I intentionally made it so that this wasn't on the graph, so that you'd have to think about it, right? I don't want you to compute numbers here, I want you to think, right? Think about the slope at -3 and the slope at -1. Which one is bigger? And the idea is, as you look at this graph, it feels like the further I go to the left, the further I go over this way, the steeper those values are. So it seems pretty clear to me that g prime of -3 will be bigger than g prime of -1 because the graph is steeper over there. The slope is going to be higher. Okay. So now, I kind of want to put together all the skills that we had on the previous one and have us talk about how to graph a derivative, like without being able to take the derivative, just to graph those tangent slopes. And so the thing to remember here is that when you are graphing the derivative, the value of the derivative, so the value of this thing, is the same as the slope of the original function. And so the way that we do this quite literally is we just walk along this function. We walk along this original function, and we just plot slopes the whole way. So if we start here at -2 and just go, so what is that slope? That slope seems pretty steep, pretty negative. I'm going to go down and call that -3. So I will put a point at -3. Right? Then we move along to -1. If I sort of picture this slope here, that's still pretty steep, but it's less steep. I mean, that doesn't feel to me like a slope of 1. Again, remember your slope of 1 should sort of be going, down 1, over 1 as you're going along. So that slope seems to me to maybe be -2 or so. Now, if you're feeling brave, pause the video, try plotting a few of these on your own and sort of see what you come up with. And what I'm doing here is I'm just going through and plotting the slope at 0, the slope at 1, the slope at 2, the slope at 3, the slope at 4. Just kind of go along and try those out. Right? So when we move along to 0, at 0, this slope right here, that seems fairly close to that slope of -1. It might be a little bit less than that, but that seems to be about -1. At 1, we have a horizontal tangent, which means the slope is 0, which means for my derivative I plot 0. At 2, I'm back to having a positive slope, and that feels like that 45-degree angle slope. That feels like a slope of about 1. So I'll plot a point at 1. Right. Over at 3, and you guys can see there's some symmetry happening here. Whatever slope is over here at +3 looks like it was the same thing that was over here at -1. So if I said -2 here, this one should be +2 on this side. And then finally over here at 4, if I go and do that last one, this is again one of those steeper slopes. The one that before I said was -3, so this one will be +3, and I'll plot my point there. And then the idea is, once you have all these points, we can tell that there is some sort of function that runs through all of them, and in this case it appears to be a straight line. So that's a general idea of how we're supposed to sketch the graph of a derivative from the graph of an original function. What we're doing is we're going along and in multiple places writing tangent lines, estimating their slopes, then plotting their slopes as the value of the derivative, and then connecting those points.